Okay, good evening, everyone. Thank you for being here. Today I will present to you my doctoral dissertation entitled Thermo-elastic topology optimization for fire-resistant reinforced concrete beams. Let's start with a very big number, 1.6 billion tons of CO2 per year from cement production, which equals to approximately 8% of the global total CO2 emissions, which is a very large contribution of the construction industry to global warming. So if you want to reduce these CO2 emissions in concrete construction, there are typically two main strategies that can be used. The first one is on a material level, where we try to reduce the amount of cement in our concrete mixtures. We can also do that by changing to different binders or using carbon curing to cure our concrete. And another approach is to look at it from a structural level by reducing the material usage as a whole. So we just use less concrete, then we also use less cement, and so on and so forth. We can do that by using structural optimization. And one form of structural optimization is topology optimization. And the question arose, what does that mean if we take into account fire exposure as well in this kind of optimization procedures? So I will first give you an overview of what I will be talking about this for the next 45 minutes. So the first part is topology optimization, which in which I will discuss why topology optimization is relevant, why is it useful, and then I will first introduce the topic to you, explain how it works for a typical structural problem, and then I will proceed to thermoelastic topology optimization, both for steady state, well, we have company, steady state heat conduction and transient heat conduction. Then the second part is about numerical investigation. Here I will develop a nonlinear finite element models to evaluate the structural performance of structures, reinforced concrete structures in fire conditions, and then apply these models to the case of the topology optimized beams that I've designed in the first part. Finally, I will end with some conclusions. So now the first part on topology optimization, which is a very big part of this dissertation. The first question is, well, that everyone has, is why topology optimization? Why does it exist, and why would you use it? So let's imagine a simple, simply supported beam with a load on top, some boundary conditions. And if you want to design a structure that is able to carry the loads to the supports, then conventionally it would be from design codes would be a solid beam, for example, that is used as a design. But what if we want to save material? We want to save approximately 50% of the material that is now in this beam. There are several options here. We can, for example, reduce the height of the beam, but then we reduce the capacity and stiffness of the beam. We can uniformly reduce the material, but then we get some kind of unrealistic, unphysical structure. Another way is to make some openings in the structure to reduce the total amount of concrete to only 50%. But these are only 3 options. There are actually many more options. So let's imagine the same beam, but we divide it into 100 elements. If we have 100 elements, we can have 2 to the power 100 possibilities, which is a very, very large number. If we then say, okay, but let's take only the possibilities where we use 50% of solid material, something like this. This is one example, but this doesn't really look like a beam type of structure. The amount of possibilities is 10 to the power of 29. This is a very big number, and I will put it on the screen just to make sure that you understand how big it is. It's a very large number, and these are all the solutions that are possible within this design space with 100 elements, only 100 elements. And if we would take a computer and calculate the performance of each of these solutions, and let's say it takes only 0.01 seconds, then it will take 10 to the power of 19 years to calculate it. This is longer than the Earth exists, so it's very large number. It's also the same number of sand particles on the entire Earth. So just to put that into perspective. By using topology optimization, we can actually reduce the number of possible solutions to only maybe 1,000 or 100 by only selecting those options that are relevant to our problem. So, and then it would maybe only take 100 seconds to come up with an optimized design. For this part, there are some research objectives. The first objective is to develop topology optimization procedures involving thermomechanical loads, considering steady state or transient heat transfer. And then when we have developed these procedures, we also write some codes and distribute these codes for educational purposes and further research. So I've told you why topology optimization would be a very interesting tool or technique to use for structural design, but now I will explain to you how it actually works. So imagine the same simply supported beam problem. I will come back to this problem many more times because it's just an easy problem. We want to, for example, optimize a structure to make it the stiffest possible structure that can exist in this design space. Okay, then instead of randomly selecting a possible solution, we're actually going to look at it from a structural perspective and set some rules. So let's formulate this optimization problem first. We want to obtain a structure that is the stiffest possible structure within the design space. So we are going to minimize a compliance objective. Compliance is the inverse of stiffness, how much a structure deforms. And we want to minimize the structure by changing the design variables x, which represent our structure. The x is a vector, contains all the solid or either no material elements that were present in the other example. These values of the design variables are restricted to a range between 0 and 1. And as you can see here, the black material represents solid material and the white material is a void material or just simply air. Only setting an objective is not enough, so we will set some constraints. The first one is the volume constraint, which says that we are going to reduce the material to only 50% of the original volume. Secondly, we are also going to add an equality constraint to ensure mechanical equilibrium and also to calculate the displacement in our structure, which will be used. The displacement will be used to calculate the objective. So this is a typical compliance minimization topology optimization formulation. Then there are several aspects that I want to discuss here, and I will highlight two of them, or several aspects that are relevant to topology optimization. And the two that I want to discuss here in this presentation is the material interpolation and sensitivity analysis, because they are key aspects to topology optimization. So the first one, material interpolation. Why do we need it? Because we want to relate our design variables to the material properties of the materials that we will use in our structure. So for example, the solid material represented by an x value of 1 will represent an element that has the stiffness of concrete. And similarly, for a value of 0, it will represent an element with the stiffness of air, which is practically 0. Then we need another tool, which is relaxation, to actually, instead of having this discrete set of choices between materials, we have an entire spectrum of materials that we can choose from. And this will be used in the sensitivity analysis to actually be able to differentiate our objective and of course constraint and to efficiently go to an optimized design. So we have this intermediate material which has values between 0 and 1. And then the materials are interpolated using a SIMP approach, which is a typical formulation that is mentioned here with a penalization factor. And this is visualized in this graph. So if we use this SIMP interpolation, we can have a material that has a stiffness that is, for example, much lower than what the density is. And this ensures that we actually, if we optimize the structure, we're going to steer it towards a 0 and 1 design. So a black and white design, which is easily manufacturable compared to a design that would also contain these gray materials. These are more difficult to manufacture or even non-existent. Then the sensitivity analysis was also a key part of topology optimization. I'm using the adjoint variable method to obtain an expression for the sensitivities. And what are these sensitivities? Sensitivities actually explain what the change of the compliance objective or the stiffness is with respect to the change of the design variables. In other words, what is the influence of changing the element's pseudodensity on the stiffness of the structure? So if we know, it essentially says which elements to change in what direction to obtain a stiffer structure. And this is then an input. These sensitivities are inputs for the gradient-based optimization algorithm that will be used in our optimization procedures, which in my case is the method of moving asymptotes, or MMA. So now I will just run through a very simple example to make you familiar with an optimization procedure. So we first start with an initial material layout. Can be any kind of material layout. Here it was chosen to start with an uniform distribution of approximately 40% of material. And based on this initial material layout, we can calculate structural response. And this is the displacement field of this structure. So we can calculate the structural response and use the displacements to calculate the objective function. The next step is to calculate the sensitivities, which we have derived earlier. And these sensitivities are then used to update our material layout, so the X. So if we then go to the next iteration, you will see that the structure already changed a little bit. This is a little bit darker, this is a little bit darker. And based on this design, we're also going to calculate structural response again, and the objective and the sensitivities, and we update our material layout once again. And we do that one more time and even more times until we actually get a structure that represents a solid and void material layout. So it's an iterative process, but in the end we will obtain a structure that is optimized for stiffness in this case. So let's go back to the original problem, or the original geometry at least. And if we then apply this algorithm, we get something like this, which is a little bit nicer looking than the previous example. But this is what we do with topology optimization. So now that we all understand topology optimization, I will go on and explain to you what thermo-elastic topology optimization is, considering steady-state heat conduction. So thermo-elastic topology optimization is simply just the same as what I've told you just now, but now we are also going to consider the possibility of thermal loads. And these thermal loads can be a consequence of fire exposure. So as you can see, what I visualized here was just the temperature increase in our structure. So what is the influence of this temperature increase on our optimization problem? We need to account for thermal expansion, for example. So and that's exactly what we are going to do in the optimization formulation. So here is a similar structure, but now we have an additional equation here, which represents thermal equilibrium, the steady-state heat conduction equation. And this equation allows to calculate the temperature field T. Using this temperature field, we can also calculate the forces in our structure that come from the thermal expansion. So there's an additional part to our loads in our structure. These are the thermomechanical load vector. In this thermo-elastic topology optimization, I've chosen to change the way we think about these materials, and I selected an insulation material for our void material or zero design variables in order to make the assumption that we only consider heat conduction in our structure rather than also considering convection and radiation. Then the sensitivity analysis, it's a little bit more complex, not that much, but it still adds 2 additional terms to the sensitivities. I will not go over the derivations, but there are 2 additional terms. The first one deals with the design-dependent load vector, because now the load vector is dependent on the design because the temperature field is dependent on the design. And the second part is the design-dependent thermal stiffness matrix, because now we not only have our standard stiffness matrix for a mechanical problem, but we have what I've called a thermal stiffness matrix as an equivalent, which includes a thermal conductivity, which is a function of the design variables. Then this mu variable is an adjoint variable, and we need to calculate it before we can actually calculate the sensitivities. So this needs to be known. We can only know what values this variable takes if we solve this additional adjoint system. So in the sensitivity analysis, or in thermoelastic topology optimization, considering steady-state heat conduction, we have to solve 3 linear systems each iterations. So first a thermal finite element analysis, then mechanical response of our system, and then for the sensitivity analysis, an extra adjoint system to calculate sensitivities, which then are used to update our design. And I will just go over the structure of such an optimization procedure. So first we start with an initial design, as I've shown already. We initialize optimization with some parameters, and then we start the iterative process. The first thing we do is update the material properties based on the material interpolation, because the design is changing all the time, so we need to update the material properties. Then we calculate the thermal response. Next, we calculate the mechanical response, then the objective function, the sensitivities, and then use the sensitivities to update the design variables. And we do this process over and over again until we reach convergence. Convergence can be defined in different ways. Usually it's defined as the maximum change in our design variables is below a certain value, a threshold. So in the end, we obtain an optimized design. So let's have a look at a numerical example to demonstrate this optimization procedure. So the numerical example is quite similar as what we've seen before, but now it's modeled symmetrically. So this is half of a beam with a point load in the middle and a heated bottom surface. If we then consider, for example, a point load of 10 kilonewtons in a temperature at the bottom of 800 degrees, and we only want to obtain 40% of the original volume, then we get a structure that looks like this. So what does this represent? It's a beam type of structure with an insulation zone at the bottom. This insulation zone is there because it wants to prevent thermal energy from the heated bottom surface to get to the structure. And this is done to actually minimize the deformation used as a consequence of thermal expansion. Then we will go over some of the influential parameters of this procedure. So first, the sensitivity analysis. These are the proposed sensitivities, but in the literature, sometimes they neglect the last term. And first I started with this type of structure of the sensitivities, and I ended up with very strange results, as you can see. The results also oscillate during the optimization, which is not favorable. And as we then compare these sensitivities, we see that for a large thermal gradient, we see that's a very big difference in these sensitivities and those. So here they actually don't take into account the entire, well, not all information that we need to efficiently optimize our structure. Then the influence of the thermomechanical load ratio. The thermomechanical load ratio is the ratio of the contribution of the mechanical load to the contribution of the thermal load of our structure. And I will show that based on two examples. So if we change the thermal gradient and keep the mechanical load constant, we start with a mechanically optimized structure. But if we increase the thermal gradient or the thermal loads at the bottom, you can see that eventually the insulation zone appears to prevent the structure from heating up. And the same we can see for the mechanical load. If we change the mechanical load but keep the thermal gradient constant, then if there's no load present, it's a very strange looking structure. But then in the end, if we increase the loads, it starts to look a little bit like a beam. And then in the end, if the mechanical load is so large, then the contribution of mechanical load to the thermal load is much larger, and we obtain a mechanically optimized structure. So the main findings of this part of the dissertation is that the proposed sensitivity analysis is more accurate, especially in case of large thermal gradients or elevated temperatures. And the thermomechanical load ratio significantly influences the results. Then also a very compact 138 line MATLAB code is made available for further research and educational purposes. And then we can move on to the optimization procedure, now considering transient heat conduction. Why is this relevant? Because sometimes thermal loads, or many times, are time dependent, or only have a short thermal exposure. So now we are going to adapt the optimization formulation to account for this transient heat conduction. So here what has changed is that now we don't consider steady state heat conduction, but transient heat conduction, which is time dependent, which is denoted by the time dependent temperature field here. And we can only calculate this, well, we can calculate this state equation by integrating it over time and subdividing it in different time steps. We also need to take that into account into our compliance objective, because now we're not interested in only the compliance of at the end of our thermal exposure, but also in the intermediate steps. So for each time step, the compliance is calculated and then summed up to obtain a complete overview during the entire time history. So the mechanical state equation is also solved for each time step. And by each time step, I actually mean that instead of applying the temperature field in one go, we do it in different smaller steps. So then the sensitivity analysis, the expression grows and grows, but this is the final one that I want to show. And there's again a new adjoint system, but now for each time step. So this means that if we want to calculate, if you want to go to the next iteration, we have to calculate 3 times the number of time steps, linear systems, that needs to be solved per iteration. So it's computationally more expensive, but I will show you why this isn't necessarily a problem. So now I will go over the same numerical example, but now instead of having a steady state, thermal steady state, we assume that our thermal exposure takes 1 hour, and it is subdivided into 4 steps. And then we get a structure that looks like this. So it looks a little bit similar, but now the insulation zone at the bottom is much smaller, thinner, because the thermal load is just less intense compared to what we had in the steady state case. And the structure resembles more of a truss-like structure rather than a cellular beam that we had before. Then first we look into the influence of the thermal exposure time, just to compare the steady state heat conduction versus the transient, or what the transient procedure can actually offer more than what the steady state procedure can. So first we start with a very short time exposure, or even just zero. So there's actually no thermal load present, and the structure is mechanically optimized. So it is as if there was no thermal load. If we then continue to make the thermal load take longer, you can see that if it takes longer and longer, it will eventually go to an optimized result that we can obtain with our steady state procedure. But all the intermediate steps are only able to be obtained with the transient procedure. If we then take a look at the influence of the time increment, then the results look very similar. And this means that we can actually just use a very coarse time integration, and we don't really need a large number of time steps to, well, it doesn't really influence the results of our optimization, at least. Then again, we look at the thermomechanical load ratio, and the results are quite similar. Not exactly, but the trend is similar. If we increase the thermal gradient, then we increase the insulation zone that is needed to prevent the thermal energy from propagating into the structure. And additionally, I've formulated a weighted optimization formulation where I added a weight factor in the compliance objective to account for different contributions of different time steps. So here we have some examples of this study. And the top left one, we have no thermal contribution. That means that I just zeroed out all the effects of the thermal loads or the subsequent time steps. And for example, the bottom right one, I increased the contribution of the mechanical load, or the mechanical part, and left the other time steps just as they were. So then you can actually mix and match a little bit to change the structure based on what you actually want to achieve with this optimization. So again, some findings about this part of the research. The thermomechanical load ratio, again, significantly influences the results. And now the transient procedure also allows more control over the exposure time, obviously, but also the thermomechanical load ratio by changing the thermal response time of the exposure time. Then I also added the weighted optimization procedure to change the thermal and mechanical contributions to the optimization. And again, a very efficient compact MATLAB code was developed and made available for further research and educational purposes. Now, onto the second part of this presentation, the numerical investigation. I will ask the same question, why the numerical investigation? Well, if we do this optimization, we make a lot of assumptions and simplifications to be able to, for example, derive the sensitivities, because it's otherwise very complex to do that. There are other reasons, but that's one of the main reasons. And some of the simplifications that I made was, for example, the material properties in our optimization problem. The materials are linear elastic and also temperature independent, which is actually very unrealistic, but it's a very easy simplification to speed up optimization, but also to develop the optimization procedure. Also, I assumed a constant thermal load, while the thermal loads can also be time dependent, as for example, fire. And also, I didn't include reinforcement in my optimization. So there's actually a need for a post-optimization nonlinear finite element analysis, and I will be doing that in Abacus, which is finite element software, taking into account more complex material behavior and more complex thermal loads and heat transfer mechanisms. So the objectives for this part are to develop nonlinear finite element models, to evaluate reinforced concrete structures in fire conditions, also to apply this model to the case of the topology optimized beams or structure that I've developed or that I designed in the previous parts. So for the numerical modeling, I've built finite element models, which are, well, there are two models. First, the heat transfer model, or the heat transfer analysis. I used a transient procedure. I also included concrete N insulation in the model to calculate the thermal response over the temperature field. The thermal properties were taken from the Eurocode, and the thermal loading was done based on a temperature time curve, and then applied to the structure by means of convection and radiation boundary conditions. The result of this heat transfer analysis would be a temperature field that describes what each point in the structure, what temperature it has. Now, the thermomechanical analysis includes the concrete and steel reinforcement. I'm using the concrete damage plasticity model in Abacus to model the behavior of concrete. I'm using the mechanical properties from the Eurocode and model code to implement that in the model. And I apply a mechanical load and impose the temperature field that was obtained in the heat transfer analysis in my thermomechanical analysis, which has two reasons, mainly because I want to include the thermal expansion, but also I want to change the mechanical properties which can be temperature dependent. So then we obtain a displacement field, and there are other outputs as well, which I will discuss in a bit. Fire conditions. So I was talking about fire conditions, and what do I mean with fire conditions? I simplified the fire to a temperature time curve, which is a very crude simplification, but it's one that is used quite often in structural fire engineering. In this case, I've drawn here the ISO standard heating regime to simulate a standardized fire test, essentially. Before using this model, I validated this against an experimental test setup done by a colleague of mine sitting here in the room. And I used these experimental data to actually verify whether my model was actually accurate enough to proceed. So here's the thermal comparison. I looked at the reinforcement temperature and the surface temperature of the concrete, and I compared it first against another model in software for fire calculations, SFE, and then also against the data from the experiment, which actually have very good agreement. Also, the mechanical comparison was done based on the deflection of the beam and the midspan deflection. And then again, we have quite good agreement between the numerical models and the experimental data. Okay, let's move on to the last part of my presentation, which is the evaluation of the fire resistance of the topology optimized reinforced concrete beams. So first I will go over the methodology. We want to compare these topology optimized beams against something that is already done, or already known, which is a reference beam conventionally designed based on Eurocode. So first, for these reference beams, going to determine the cross-section and material properties, then calculate the ambient design capacity. So when does it actually fail, these beams? Based on this ambient design capacity, I will determine an ambient preload, which will be used in my fire analysis to assess the structural fire resistance of the beam. And for the optimized beams, the optimization was done based on the previous chapters, of course, but also taking into account this problem setup. Again, we calculate the ambient design capacity, which can only be done by using these finite element models because the geometry is quite complex and it cannot be simplified. Then we determine the ambient preload to calculate eventually the structural fire resistance. Now, there are two case studies that I will go over. The first one is a case study based on equal preload, which means that we're going to define a preload based on the ref beam, which I will discuss in a minute. One of the reference beams, I will just keep the preload constant for all beams. So every beam will be loaded with the same load. And this is based on 70% of the ambient design capacity of the ref beam. In the second case study, I will compare the beams based on equal utilization, which means that I will be adapting the ambient preload based on the capacity of each beam itself, which can make for a fairer comparison. So then the beam designs, so two reference beams. This is the original reference beam with only 50% of the material within the design space. This is the ref full beam, which actually takes up the entire design space. So this would be 100% and this would only be 50%. And the design is based on tabulated minimum dimensions from Eurocode 2 based on a structural fire resistance rating of R120, which means that it would maintain stability of over 120 minutes. Then the optimized beams are all optimized for 50% of volume reduction. There are three different optimized designs. The first one is structurally optimized. So let's say the first chapter or the second chapter. The second one is a steady state optimized design, TOSS. And then the last one is transient optimized. So in the beam designs, for the reference beams, it's easy to actually come up with this geometry, but for the optimized beams, based on the optimization, we actually get an image, just some pixels, and then we have to translate that into CAD geometry to actually include that in our finite element software. I also used the medial axis theorem to come up with a reinforcement layout automatically based on this geometry. So first we will look at the ambient design capacity of our beams. I'm plotting here the plastic strain distribution in our beams to see what the failure mode is of those beams. So here the reference beams, they appear to have a lot of bending cracks, and finally at peak load you can see that there's failure in the middle of the beam. You can also see that this is the reinforcement, by the way, that the reinforcement starts yielding. For the optimized beams, the failure mode is quite different. So in many cases, the failure is located in the joint regions or at the supports. And if we can compare these load displacement curves, we can see that the reference full beam actually has a much higher capacity than the other beams, but makes sense because it uses the entire design space. So it's a much higher capacity. The reference beam has approximately half, which also makes sense. Then the structurally optimized beam has a capacity that's quite similar to the reference beam, but yeah, the failure mode is completely different. Then the transient optimized beam has a significantly lower capacity compared to the reference beam, and then the steady state optimized beam is mostly designed to have thermal loading, so the capacity is much lower. If we then take a look at what happens in the fire analysis, then we see for the reference beam, based on the applied ambient preload, it fails during the 4-hour exposure, around approximately 3 hours, while the reference full beam doesn't really fail during this fire exposure, so it maintains stability. The temperature field in both beams is the same. You can see that it's very much located at the bottom and doesn't really go entirely to the top. Then the optimized results, again plotting the plastic strain distribution. Similar looking structures and failure modes. So here the structurally optimized beam fails at the supports, and the joint regions, the steady state optimized beam also at the support regions, and then the transient optimized beam has very large cracks, but it doesn't really fail during the fire exposure. You can also see that in the structurally optimized beam, the temperature increase in the structure is much higher than, for example, in the case of the transient optimized beam, because this also includes the insulation layer, which is not present here. So if we then look at the displacement time curves, so how does the structure deform or deform over time during the fire exposure? You can see that the transient optimized beam actually maintains stability during the 4-hour exposure with a limited deflection. The reference full beam also survives or maintains stability, but it doesn't. It deflects much more than the transient optimized beam. The structurally optimized beam already fails after approximately 90 minutes, and then the reference beam fails after 3 hours. The steady state optimized beam is not really present in the structure because it actually already failed in ambient conditions, so it lives here somewhere. And this can be attributed to the fact that the ambient preload in case of in this first case study is always equal. It's always the same, and in case of the steady state optimized beam is actually 200% of its design capacity. So it's much larger, and it makes sense that it actually fails already. So the main findings of this part of this case study are that the reference beam performed better than the tabulated fire resistance of R120. So that's a good thing. Then the structurally optimized beam has the same capacity or similar capacity to the ref beam, but it has a lower fire resistance. And then the steady state optimized beam fails in ambient conditions already, and the transient optimized beam just maintains stability during the 4-hour exposure. But mainly because of this steady state beam, we want to also look into the second case study under equal utilization to give it a fair chance of surviving the fire. So again, we show the plastic strain distribution for all beams. And now we can see that both the reference beam and the reference fill beam, they both fail during the fire exposure, because now the reference beam is still loaded in the same way, but the reference fill beam has a load that corresponds to 70% of its capacity, which is much higher than in the first case study. Similarly, for the steady state optimized beam and the transient optimized beam, here the loads are much lower than in the first case study. So they actually maintain stability throughout the entire fire exposure. Then I will, no, what I was going to say. Here I've plotted the displacement time curves again, but now for a second case study. And here you can see that the transient topology optimized beam and the steady state optimized beam maintain stability throughout the entire fire exposure because they are just loaded much less than before. Steady state, the structurally optimized beam just a similar result as before. And then the reference beam both fail at the same time because of the same geometric properties of the cross-section. So main findings of this part is that the reference beam have the same similar time to failure, which is something that we would expect actually, but it's nice to see that it actually is a result from these numerical analysis. Then the structurally optimized beam has a lower fire resistance compared to the other optimized beams, which is quite important because it makes sense that it has been useful to do to apply the thermo-elastic topology optimization to this problem and to see that it actually has a higher fire resistance. And then the last part is that the thermo-elastically optimized beams both maintain stability throughout the entire 4-hour fire exposure under the assumption of equal utilization. So then finally the conclusions. I've already mentioned them, but I will just go over them once more. So for the topology optimization part, I've developed steady-state and transient thermo-elastic topology optimization procedures. I've also made some MATLAB codes and distributed them for further research. The thermomechanical load ratio in both cases significantly influences the results, and the transient procedure actually has a benefit to offer more control over the thermomechanical load ratio. Then the second part on the numerical investigation, I've developed nonlinear finite element models to evaluate structures in fire, concrete structure in fire. I use these models to evaluate structural performance of topology optimized beams in fire. It appears that the optimized beam have a lower bending capacity than the reference beams, and the thermoelastic optimized solutions offer a higher fire resistance, provided that we compare them under equal utilization. So that was it. Thank you.